300,000 tons of carbon dioxide are released into the atmosphere annually by the traditional production of steel and concrete for infrastructure. Why would engineers in rural India choose a soft, biodegradable fabric over these massive, heavy, and expensive industrial materials? It seems like a simple question of resource availability, but in reality, the use of coconut fibers provides a structural foundation that rivals synthetic geogrids. Coir Geofabric transforms from a raw organic husk into a stabilizing layer capable of supporting heavy trucks and millions of individual journeys. One can notice how the thick, fibrous outer shells of coconuts are harvested and diverted from waste streams into industrial processing lines. The process is only gaining momentum. This organic matter is stripped, cleaned, and woven into high-tensile nets that act as a quiet, unseen reinforcement beneath the soil. But such industrial shifts toward natural materials come at a price of rigorous technical preparation. The camera glides along the automated looms, where the coarse brown fibers are twisted into uniform ropes before being interlaced into the final fabric. At first glance, a coconut seems too fragile for such a role, but in reality, the high lignin content of the coir prevents it from decaying immediately when buried in moist earth. This allows the roadbed to stabilize and the soil to settle long before the organic reinforcement eventually degrades back into the landscape. 100 kilograms of coconut husks yield approximately 35 kilograms of the long, durable fibers needed for road-grade geotextiles. Workers at the processing stations sort the raw material by length and thickness to ensure the resulting mesh can withstand the sheer pressure of heavy machinery. Everything only gets more complicated when the fabric is transported to construction sites across the countryside. It is visible how the large rolls of brown mesh are unrolled over the graded earth like a protective skin. The material lays in an even layer across the dirt before being covered with stones and local aggregate. This sandwich of organic and inorganic layers creates a composite structure that prevents the road from sinking into the soft Indian soil. The process does not end at this stage. Because the coir is naturally resistant to salt water and microbial attack, it remains functional for several years, providing the critical support needed while vegetation grows through the mesh to permanently bind the earth. This transition to a biological reinforcement system ensures that the infrastructure becomes an extension of the local environment rather than a permanent scar of concrete and asphalt. The material is ready to move to the next processing phase without haste. 100% of a road's operational lifespan depends on factors far beyond the visible asphalt or concrete surface. Why does the structural integrity of a massive highway rely on a hidden foundation buried deep underground? Most motorists never realize that a layer only a few millimeters thick determines whether the entire construction above will remain stable or eventually crack and collapse. Coir geotextile fabric serves as this critical, invisible barrier within the earth. It only looks obvious that synthetic materials are required for such strength, but in reality, this fabric is woven entirely from natural coconut fibers. The material contains zero synthetic plastics, no artificial polymers, and absolutely no petroleum-based components. One can notice how the coarse brown fibers create a dense grid originating from a single biological resource, the discarded coconut husk. Everything only gets more complicated when analyzing the specific role these materials play in civil engineering. Geotextiles are not secondary or optional additions to a project. They are strategically placed between the weak subsoil and the heavy structural layers above to perform four critical mechanical functions. The process involves controlling the horizontal and vertical water flow, stabilizing the shifting soil base, distributing massive vehicle loads across a wider area, and preventing internal erosion. But this is just the beginning. It is no coincidence that Coir Geotextiles have seen such massive adoption across the geography of India. The country possesses a unique combination of environmental and economic conditions that make this bio-based material exceptionally suitable for large-scale development. Many rural areas across the subcontinent are characterized by weak soil foundations that cannot support heavy traffic without reinforcement. Tropical climates bring heavy seasonal rainfall that can wash away unprotected roadbeds in a matter of weeks. One can notice the equipment gradually clearing paths for new transit corridors while infrastructure budgets remain strictly limited. Instead of relying on expensive imported polymer geotextiles made from oil, the regional industry utilizes its own abundant natural resources. The camera glides along the vast coastal regions where millions of coconut husks are processed into high-strength netting. The fibers are spun into thick yarns that resist rot even when submerged in damp soil for extended periods. This provides a cost-effective and environmentally neutral solution for stabilizing the ground before the first ton of gravel is even poured. The material is laid in wide, overlapping sheets that grip the earth with a high coefficient of friction. Thus, the foundation reaches the required standard, transitioning into a calm stage of preparation for the upper pavement layers. 19 billion coconuts are harvested every 12 months across the southern regions of India. Why is this specific tropical territory so critical for the production of geotextile fabric? The answer lies in the massive concentration of raw material, as this single area generates more than 60% of the country's total coconut output within a climate that remains hot and humid throughout the entire year. One can notice how the plantations form a complete economic ecosystem for local communities. The trees support millions of livelihoods by providing materials for the food, beverage, and construction industries simultaneously. Each mature coconut tree yields between 50 and 80 fruits per year, provided the climate remains stable. But this is just the beginning. Harvesting occurs when the fruit reaches an age of 11 to 12 months. At this precise stage, the husk is mature enough to contain long, strong fibers with a high concentration of lignin. Large plantations operate on continuous cycles of 30 to 45 days to maintain a steady flow of material for processing facilities. Manual labor remains the primary method for gathering the harvest in these dense groves. Skilled workers climb trees reaching heights of 8 to 15 meters without the use of safety harnesses. They cut down entire bunches, allowing the fruits to fall freely toward the plantation floor. One can notice how the ground must be kept entirely clear during this phase. Each individual coconut weighs between 2.5 and 3.5 kilograms. Therefore, the impact zone must be monitored to prevent accidents or equipment damage. It gets more complex further on. Workers utilize long cutting poles measuring 8 to 10 meters to reach the highest branches from the ground in areas with difficult terrain. This method increases safety for the laborer, but it causes the coconuts to strike the earth with much greater force. Such impacts against rocks or roots can crack the protective husk and degrade the quality of the internal meat. Transition to the next level. Immediately following the harvest, the fruits are moved to collection points located along major roads. Here, the separation of the husks begins. At first glance, the coconut water and white flesh appear to be the most important components, but in reality, the geotextile industry focuses exclusively on the thick outer layer. 35 to 45% of the total weight of the fruit is concentrated in this husk. It measures between 5 and 7 centimeters in thickness and contains millions of fibers bound by natural lignin. This structure is naturally resistant to biological degradation and remains exceptionally tough under mechanical stress. The process is only gaining momentum. Metal spikes and pointed stakes are used to secure the coconuts during the manual dehusking phase. Workers utilize specialized knives to peel away sections of the outer husk from the hard inner shell with rapid, rhythmic movements. A single skilled laborer can process between 500 and 1,000 coconuts in one day. Everything only gets more complicated. Tens of thousands of units are processed daily at large-scale collection centers. At this specific stage, the husk remains rough and moist, making it completely unsuitable for immediate construction use. Yet this material serves as the physical foundation for roads designed to endure decades of extreme weather. One can notice the high moisture content of the raw husks, which often exceeds 60%. It seems simple to move directly to mechanical processing, but in reality, feeding wet husks into machinery would be disastrous. The internal fibers would break or tangle, instantly losing the tensile strength required for the finished fabric. The heavy raw material must now undergo a transformation to stabilize its internal structure. The journey of the fiber toward its final form continues. 2 to 4 weeks is the specific duration required for the raw husks to remain in open drying yards under direct sunlight. This period fluctuates based on the current season and specific weather conditions at the site. Why is this prolonged exposure to the atmosphere considered a mandatory requirement for the raw material? Natural drying is the only method that gradually lowers the internal moisture content to 15% while simultaneously softening the natural lignin structure of the husk. This physical transformation creates the ideal mechanical state for the subsequent separation of the fibers. The process is only gaining momentum. Automated extraction machines receive the dried husks once the moisture reaches the designated threshold. Inside these industrial units, rotating shafts and heavy rollers exert mechanical force to tear the husk apart. This action effectively isolates the long core fibers from the pith and other natural impurities. One can notice how a clear stream of coarse material begins to form as it emerges from the extraction system. It only looks obvious that the fibers are now ready, but in reality, they still harbor enough moisture to remain vulnerable to biological degradation. 3 to 7 days of additional drying are required to bring the moisture levels down below 5%. This specific threshold is critical because it prevents the development of mold during long-term storage and significantly reduces the weight of the material. By reaching this state, the fibers maintain their mechanical properties and gain long-term stability. The equipment gradually moves the stabilized material toward the spinning stage. Spinning machines operate without interruption to transform the loose mass into uniform strands. These units straighten the fibers and apply a constant twist to ensure every strand possesses a consistent tensile strength. Such mechanical processing prevents the material from tangling or snapping when it eventually moves to the weaving looms. It is visible how the loose fibers become a structured thread capable of bearing significant industrial loads. But this is just the beginning. The load-bearing capacity of the final geotextile fabric depends entirely on the precision of this twisting phase. Large spools receive the dried and twisted core fiber bundles before they enter the specialized industrial looms. Within these facilities, the warp yarns are stretched in parallel to establish the primary structural framework of the fabric. Simultaneously, the weft yarns are interlaced at specific, regular intervals to create the distinctive mesh pattern. One can notice the rhythmic movement of the machinery as it produces between 200 and 300 meters of fabric every hour. The process is only gaining momentum as the weaving density determines the final output speed. 10 to 25 millimeters is the standard range for the mesh openings in the finished material. This specific spacing allows rainwater to pass through the fabric freely while ensuring the underlying soil remains stable. On average, 100 kilograms of processed core fiber yields approximately 250 to 300 meters of fabric with a width of 1 meter. Everything only gets more complicated when the production shifts from automated factories to traditional settings. Rural areas across India continue to produce these geotextiles using manual labor and simple mechanical looms. In these environments, the entire outcome rests on the individual skill and physical experience of the weaver. The technician must manually set the tension of the warp fibers and carefully control the spacing of the mesh. At first glance, the method seems primitive, but it allows for extreme adaptability to unique terrain requirements. A steady rhythm must be maintained while passing the weft through the frame to ensure consistency. While an industrial loom produces hundreds of meters, a hand weaving operation may only output a few dozen meters in a single day. Once the weaving is finalized, the fabric undergoes a rigorous quality inspection to check for structural integrity. The material is then rolled into large, heavy coils and prepared for immediate transport to various construction sites. The journey of the raw husk concludes as it transforms into a finished engineering tool. 100% of the structural integrity of a modern roadway depends on the hidden layers beneath the asphalt. Why is the preparation of the ground so strictly regulated before a single roll of fabric is unfurled? It would seem that the geotextile could simply be laid over the raw earth to provide reinforcement, but without a perfectly leveled and compacted subgrade, sharp stones or jagged debris would puncture the synthetic fibers under the weight of heavy machinery, rendering the entire separation layer useless. Engineers oversee the mechanical leveling process to eliminate every uneven spot and protrusion. Large rollers traverse the path multiple times until the earth reaches a specific density. One can notice how the soil transforms into a smooth, hardened plateau capable of supporting the engineering functions of the material. But this is just the beginning. The rolls of geotextile fabric are positioned precisely at the designated starting point of the construction sector. Laborers or mechanical dispensers unroll the material strictly along the center line of the future road. It is visible how the fabric lays in an even layer, pressed firmly against the soil surface to ensure there are no air gaps or structural folds. At every joint, the edges of adjacent sheets are overlapped by several inches to create a continuous, unbroken barrier. This ensures that both physical loads and subterranean water flow are distributed evenly across the foundation. It only looks obvious to lay the material down, but in reality, the fabric must be temporarily immobilized. Steel stakes or specialized pins are driven through the edges to hold the position during the subsequent phases of heavy construction. The process is only gaining momentum. Successive layers of coarse gravel, graded soil, and crushed stone are spread directly over the synthetic reinforcement. One can notice the rhythmic movement of loaders and spreaders as they deposit hundreds of tons of aggregate. Each lift of stone is thoroughly compacted, sandwiching the geotextile between the subgrade and the base course. Because of this specific reinforcement layer, the finished road gains a significantly higher load-bearing capacity. The fabric acts as a structural bridge, preventing the intermixing of soil and stone while distributing the weight of passing vehicles. Everything Everything only gets more complicated as the final asphalt paving begins, but the foundation remains stable. Consequently, the pavement develops fewer surface cracks and maintains a longer service life even when subjected to harsh climatic shifts and extreme temperature cycles. The material is ready to move to the next processing phase without haste. 100% of the coconut is utilized as the white flesh inside the shell initiates an entirely different value chain, while fibers become the foundation for industrial roads. Why is the processing of the internal pulp divided into such distinct thermal and mechanical stages? The initial stages of dehusking appear straightforward as a manual or semi-automated task, but in reality, the preservation of chemical integrity requires that only coconuts meeting strict food-grade standards proceed to the specialized oil extraction facilities. This ensures that the resulting lipids maintain their biological value and molecular stability during the transition to the next level. The equipment gradually cleans and washes the separated flesh before it undergoes a controlled drying process. One can notice how the white material moves along conveyors toward high-pressure units for mechanical or cold pressing. This extraction method is engineered to maximize the total yield of virgin coconut oil while simultaneously protecting the natural aroma and delicate fatty acids. Everything only gets more complicated as the oil is filtered and stabilized for diverse industrial applications. The liquid serves as a primary raw material for cooking oils, skincare formulations, and even specialized bio-based lubricants used in heavy machinery. In India, this clear liquid represents one of the highest value products derived from the agricultural sector. The process is only gaining momentum as it contributes a significant percentage to the total income of both the local growers and the massive processing plants. It is visible how even the solid coconut cake remaining after the oil is pressed out does not exit the production cycle. Instead of being discarded as waste, this nutrient-dense byproduct is repurposed into organic fertilizers or high-protein animal feed. This secondary utilization effectively closes a critical loop in the material resource cycle. Alongside the extraction of oils, the movement of whole fruit coconut water is rapidly emerging as a high-growth value stream. Immediately following the harvest, young coconuts are subjected to a rigorous selection process based on size and shell integrity. It only looks obvious to crack the fruit immediately, but in reality, the most valuable export products require the liquid to remain sealed within the natural shell. The surface is hygienically treated and cleaned to preserve the original shape of the fruit without any structural compromise. But this is just the beginning of the preservation sequence. The entire fruit is subjected to light pasteurization or rapid chilling to extend the shelf life of the internal minerals and electrolytes. In modern processing facilities, one can notice how tens of thousands of fruits per day are sorted by automated weight sensors. The equipment moves at a constant speed as each coconut is labeled, wrapped in protective film, and placed into reinforced export cartons. These units are shipped in high volumes to markets in the Middle East, the United States, and Europe. Consumers in these regions prioritize the direct experience of drinking from the fruit with minimal industrial intervention. From the synthesis of construction materials to the extraction of food-grade beverages, coconuts in India do not follow a single linear path. The process branches into multiple parallel value streams that serve chemical, cosmetic, and pharmaceutical industries simultaneously. All of these high-value outputs originate from the same agricultural resource through a meticulously managed series of mechanical and thermal steps. Thus, the material reaches the final phase of its global distribution cycle through these complex industrial layers. 100% of the raw material used for these geofibers once existed as a discarded byproduct abandoned on the periphery of tropical plantations. Why did such a humble organic waste travel through a complex industrial chain to become a critical component buried beneath modern roadways? It would seem that synthetic polymers would be the only choice for reinforcing heavy infrastructure, but in reality, the natural resilience of the husk provides a structural stability that petroleum-based alternatives struggle to match over long periods of environmental exposure. The trajectory of this coconut-based engineering material represents more than a narrow advancement in civil engineering. It serves as a physical demonstration of a shift in industrial logic, where humanity seeks technical solutions within biological cycles. One can notice how the equipment processes these rough, coarse fibers into dense protective mats that shield the earth from erosion. The transition to the next level of sustainable construction is already gaining momentum. As the global industrial complex faces the depletion of fossil resources and the acceleration of climate change, these botanical structures offer a functional alternative. It is is visible how the brown, lignin-rich fibers are woven into high-tensile grids that stabilize soil without leaching chemicals into the groundwater. Everything only gets more complicated when considering the scale of global infrastructure. It only looks obvious to use traditional plastics for soil reinforcement, but the raw strength found within the casing of an ordinary fruit proves that simplicity often aligns with technical efficiency. The process does not end at this stage. The application of these organic fibers across various heavy industries suggests a broader model for repurposing diverse agricultural residues into high-performance industrial assets. The machinery gradually lays the finished fiber mats in an even layer across the construction site, where they are covered by tons of aggregate. This concludes the primary transformation of the material from a plantation waste product into a permanent structural element. The organic material is now ready to perform its function for decades as part of the silent foundation of the transport network. Thus ends the transition from a simple botanical byproduct to a sophisticated engineering solution.